In this video, we're going to be looking at locating the real zeros for polynomials and finding all those zeros. So we're looking at the local behavior as we have already checked out the end behavior of these polynomials, and you have some good ideas about how to find these zeros now. So this section will talk more about the existence of zeros and more about how to find and graph these. So this is putting together our big picture for polynomials. It starts out with one of the biggest theorems of algebra called the Fundamental Theorem of Algebra. What it says that if we have a polynomial of degree n, that it has to have at least one zero. So what that means is if f is a polynomial, we set it equal to 0, we have at least one root or solution, one zero, um, to our polynomial. Now we need to note that it may be a non-real complex number, so we might not even be able to see it cross the x-axis there. So we could have like something like 5 plus 2i. Okay. Note that this theorem is an existence theorem. It tells you that zeros exist, but it doesn't tell you how to find them. Luckily, we've talked about methods to find them. So now we can use this fundamental theorem of algebra to tell us that they exist. In fact, it turns out that by the linear factors theorem, which comes from the fundamental theorem of algebra, you can take any nth degree polynomial and factor it into a coefficient, like the leading coefficient, times n factors. So in fact, if we have an nth degree polynomial with real coefficients, then we will have exactly n linear factors, which means we have exactly n zeros. We want to note, though, that some of these factors could be identical. So we could have what we call multiplicity on our zeros, and we'll discuss that. So if we have, for instance, 2, and it is repeated 3 times, so we would have an x minus 2, x minus 2, x minus 2, then that 0, 2 would be counted 3 times for 3 zeros. Also, some of these can be non-real complex numbers, which means they could be imaginary. We wouldn't see those crossing the axis. Finally, what this theorem implies is that if you have an nth degree polynomial, you're looking at the graph, it has at most n x-intercepts. So those are the zeros. If they're all real, we'll be able to see those x-intercepts. And at most, n minus 1 turning points. So a turning point is where the graph will sort of switch from increasing to decreasing, or vice versa. All right, here are some sort of rules for zeros of our polynomials. This is really just different terminology. So for any polynomial function, nth degree, the zeros of f of x are as follows. So they're the values that cause that function to be 0. We set that function equal to 0. Those x values that we plug in and get 0 out are called zeros. The x-intercepts of a graph of f of x only if they're completely real valued. So a 0 can be an x-intercept of a graph. We can see it cross as long as it's a real valued function. So, or I'm sorry, as long as it's a real valued 0. So again, we're not going to see these imaginary zeros cross the axis. And finally, if we do have a 0, x is equal to a, then x minus a will be a factor of that function. So let's go ahead and look at a few sort of simple examples here. I say simple because we already have these polynomials factored out. So notice that we could, in fact, find the end behavior from the leading degree and the leading coefficient of these, but we're just looking at the zeros here. So let's go ahead and find the zeros of these factored polynomials. How do we find zeros? Well, we set that function equal to 0 and find those x values. So this quadratic has been factored, and we have x plus 6 is equal to 0 and 2x minus 1 is equal to 0. That means our zeros will be x is equal to -6 and x is equal to, if I add 1 over and divide by 2, it'll be 1/2. This one will have 2 zeros, just like the fundamental theorem tells us. The second one factors into a perfect square trinomial. In this case, we have 2x minus 3 squared. So this would be like 2x minus 3 times 2x minus 3. And when we set each factor equal to 0, I would have 2x minus 3 is equal to 0, add 3 over, divide by 2. So we would say x is equal to 3/2, but this would be twice. So we're going to say this has multiplicity 2. So this 0 is going to have multiplicity 2, which means we count it twice. So notice that the degree is 2. We need 2 zeros, and we do have one that's counted twice. This polynomial here, if we set it equal to 0, it turns out this one's not factorable, but it should have 2 zeros. So using the quadratic formula, we get 3 plus or minus I times the square root of 31 over 4 being zeros. You might notice that this is a parabola, so it does open upward because that degree is even and the leading coefficient is positive. So what's going to happen if we looked at the graph here, it's going to open upward, but it will never actually cross that x-axis. So it looks something like this. So we do have zeros here, but these are not x-intercepts because we can't see them on the graph. Let's look at these others. D, we have this cubic now, so we should get 3 zeros, and this factors into 3 distinct factors. We set each one equal to 0. This would give us plus 1 divided by 2, so x is equal to 1/2. X is equal to -5, and x is equal to 4. Those would be the 3 zeros. In E, this factors into a linear and then a linear factor that's repeated. So this would be, again, like x plus 1 times x plus 1. But we saw from above that we just know that that 0 is going to be a multiplicity 2, 0. So we know that x equals 2 is going to be a 0, and x equals -1 is going to be a 0 of multiplicity 2. Finally, we have this cubic graph here. So we're looking for 3 zeros, just like the 2 above it. But this time, if I set this equal to 0 and solve for x, I would take the cube root of both sides and get x plus 3 is equal to 0, or x is equal to -3. So it turns out x equals -3 is a 0, but it's going to be a multiplicity 3. So we do see that cubic on the x plus 3. And so the powers, really, when we factor these out, will tell us how many times we count that 0. As we do notice, some of these have what we call multiplicity. So in B, E, and F above, we have a repeated 0 or multiplicity. In a minute, we'll show you how to graph these. Okay, so we talked about some of these zeros having multiplicity. So if we look in B, we had our factored form with a power of 2. So the 0, x equals 3/2, has a 0 of multiplicity 2. In E, we have a factor of x plus 1 squared. So we can say that x minus 1, x equals -1 has a 0. of multiplicity 2 as well. Notice that it's always the power on the factor there. And finally, f, that factored into x plus 3 cubed. So in f, x equals -3 has a 0 of multiplicity 3. So in each case, we can say that these are the zeros and they have those multiplicity. So when we go and graph these, we're going to find out something happens when we have multiplicity here. So when the multiplicity is odd, like this one where x is equal to -3, the graph goes through the x-axis. So when we plot that x-intercept, the graph's going to go through there. When the multiplicity is even, like these two, where the power was 2, the graph bounces off the x-axis. And it turns out, in fact, when we have a multiplicity of 2 or greater, so if we have a multiplicity of more than 1, the graph is going to flatten out. So the graph flattens out near that 0. So if I were to plot these three, then I'm going to just graph those functions for us. If I were to plot these three, the factored function for b is going to be f of x is equal to 2x minus 3 times 2x minus 3. So that's going to actually be 2x minus 3 squared. It turns out that the end behavior, we would have an even degree polynomial, and we would have a positive leading coefficient because we originally had 4 for our leading coefficient. It's going to open up on both sides. So this is a second degree, so we should see it bouncing off the x-axis. So if we look at our end behavior, and then we know our 0 is going to be at 3/2, which is right here, it's going to act like a parabola. In fact, this is going to be a parabola. It just opens upward. And there's a nice sketch. So we have the end behavior, we have the 0 is equal to x is equal to 3/2, and notice that it bounces off that x-axis. So locally, when we're looking for these zeros, it actually is going to behave like the power on the factor. So this power on the factor is a square, so it behaves like a parabola at that point. Let's look at e. So e was factored as this. So h of x is equal to x minus 2 times x plus 1 squared. So again, this has a degree of 1, 2, 3, and the leading coefficient's positive. So we know that the end behavior looks like this. It's going to go up to the right and down to the left, just like a line. We're going to sketch the zeros here. So at x is equal to 2, we have 0. But notice the power on this is 1, so it's just going to go through the graph. And at x is equal to -1, we have a 0 of multiplicity 2. So we know that that's going to bounce off the graph here. So our end behavior tells us what's going to happen to the left and the right of these zeros. And then we should see here that this one, since it has multiplicity 2, which is even, it's going to bounce off the x-axis. So a sketch of our function here would look like going up, hitting, coming back down, and then it has to look like this for the end behavior. So it's going to eventually come back up through the other 0 and exhibit that end behavior. So we see here at x is equal to -1, we're going to have that bouncing behavior just like a parabola. Whereas right here at the other 0, this has a power of 1, so it's going to go through just like a line. So it's neat to see how these factors can sort of give us the local behavior there. Finally, f of x, or f, was h of x is equal to x plus 3 cubed. So these all sort of had the similar in behavior in terms of the function being a positive leading coefficient, and this one has an odd degree. So the in behavior is going to look just like number 2 there, the last one. And there's only going to be 1, 0 repeated 3 times. So this one, the multiplicity is 3, which is odd. So it's going to go through the x-axis. So how does it differ from this one? Well, if I go over here and plot at -3, if you graph this, you will see that as we get closer and closer to that 0, our graph is going to flatten out quite a bit. It's going to look just like a cubic, because really that's what that factor is. It's a cubic. So you see that it's going to flatten out a little bit compared to here. This is flatter, and it goes through the function. So that's what happens if that 0 is equal to x equals -3. All right. So in our last set of exercises here, we're going to look at finding those zeros. Okay, so now we are going to be given functions that aren't factored, and we're going to be tasked with finding all those zeros and factoring the function out. I did the first one for you just to sort of illustrate the process that we will do. So in the first one, what I did was I found the in behavior, which is not really important for this exercise, but it will tell us the holistic approach of graphing this function. And then I use that rational zero theorem to find the factors of the constant term, or the factors of the leading coefficient, to find the possible rational zeros. The next thing I did was plot that, my calculator, and I found that I thought that -3 was a 0. So when I find that 1, 0, I need to break this cubic down into quadratic. I divided that -3 in synthetically. These are the coefficients here of my polynomial in order. And notice that I did get a 0 for a -3. And I used the quadratic formula for this extra factor remaining that was quadratic. And that's how I found the 3 zeros. And then I can go ahead and turn those into factors. Let's look at B. So I'm finding the factors of this polynomial. I note that it's degree 3, so I'm going to find 3 zeros. The rational zero theorem would say if the zeros are rational, so I'm going to say possible rational zeros, they're going to be equal to plus or minus the factors of that leading, or of that constant term. So 6 has factors of 1, 2, 3, and 6 all over the leading coefficient. So factors of the leading coefficient are just plus and -1. So if our zeros are rational, they will be one of these eight choices. Now what I do is I go ahead and plot that polynomial. Here it is. I'm looking at some zeros here, so it looks to me like -3 might be a 0. And notice that that is in our list. I notice that -1 might be a 0, and that's in our list. And I notice that 2 might be a 0, and that's in our list. So I just choose one of these and I divide it in. So I'll just start at the left point. What I'm going to do is I'm going to do a trace just to make sure. I'm going to plug in -3, and it does say 0. So I'm going to use that to go ahead and divide in. I'm going to have -3, and then my coefficients are 1, 2, -5, and -6. So I'm going to try to factor this down by synthetic division. Bring down my 1 times -3, add, multiply, add, multiply, add, and I get this 0. So that's great. I know that x equals -3 is a 0. And what I have left is x squared. So these are the coefficients of a polynomial 1 degree less than the one given because I factored out that x plus 3 or that minus 3. So I'm going to have x squared minus x minus 2. And so really what I know is for this 0, I have x plus 3 as a factor times this polynomial here. And as we saw, this one probably factors. So I could use the quadratic formula. I sort of saw this one factors. And so I'll just give it a try because it has to be x and x to give us an x squared. I need two things that multiply to -2 but add to -1. How about a -2 and a 1? That's really fits the ticket. So this is going to be my factored polynomial. And if I set this equal to 0, I note that my zeros are at -3, 2, and -1, just like I saw on my graph. -3, -1, and 2. Okay, a lot of them aren't this easy, but the process is sort of the same. With that in mind, let's take a look at this next one here. This is also a third degree, so I'm going to find 3 zeros. And I'm going to list the possible rational zeros. So now I have the factors of 52 over the factors of 1 again. The factors of 52 are 1, 2, 5 plus 2 is 7, so 3 doesn't go into it. 4 does. And then 4 times 13 is 52, and 2 times 26 is 52, and 1 times 52 is 52. I don't think 6 goes into it. 5 surely doesn't go into it. 7 doesn't go into it evenly. So we know that these are the only factors. And again, over plus or minus 1, we'll just get these. But now we have a lot more. We have 1, 2, 3, 4, 5, 6 doubled because it's plus or minus. So we have 12 possible zeros. I'm going to go ahead and give this guy a sketch. So I'll go into my y equals. We'll do x cubed minus 2x squared minus 11x plus 52. And graph it. All right, I see 1, and that's all it takes. So, you know, I'm looking for 3 zeros. I only see 1, but if I can factor that in, then I can find the other 2 by the quadratic formula. So this one looks like it's at -4. Just to be sure, I'm going to go ahead and push trace and type in -4. Yep, -4, 0. So -4 is going to work for us. I'm going to go ahead and use synthetic division here. So the process is sort of the same every time. Also, I should note that -4 would be in the list. So I'm going to have success here. So 1, -2, -11, and 52. Those are my 4 coefficients. I'm going to divide them by -4. I bring down the 1, multiply, add, multiply. 24 minus 11, that's 13. And if you play cards, there's 13 cards in each suit times 4. That's -52. 52 cards in a deck, and you add and you get 0. So we see that, yeah, x plus 4 is a factor because we have 0 as our remainder. And that's going to be times x squared minus 6x plus 13. So this should factor down into a couple more zeros, but actually it doesn't factor. We couldn't see it on that window, and I'm not really sure of anything where I multiply two things together, I get a plus 13, but I get a negative 6. The only factors of 13 are that. So I can use the quadratic formula to solve for the other two zeros. I'm going to do that. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. That will give me 6 plus or minus. So I have 36 minus my 52. 36 minus 52 is negative 16 all over 2. I have the square root of a negative. That's that I we can pull out. And the square root of 16 is 4. So this is going to be 6 plus or minus 4i over 2. And these are all even. So if I'm careful, I can cancel things out. 6 goes into 2 3 times, but I have to, since I'm adding and subtracting, divide in 4 as well. So I get 4 divided by 2 is 2i. So my other two zeros are going to be 3 plus or minus 2i, as well as this x is equal to negative 4. When I look on my calculator, I won't be able to see these zeros because they're imaginary. I won't be able to see them as x-intercepts. So I have one x-intercept, but all three of these are zeros. It has to be because this is a third degree polynomial. So when I totally factor this out, I have x plus 4 times x minus one of those imaginary zeros times x minus the other imaginary zero. Sort of notice here that when we get these zeros, they always come in their conjugate pairs. So if we have an imaginary zero, we're always going to have the plus or minus 2i. So if we have 3 plus 2i, we'll also have 3 minus 2i. I'm going to take a little break here and we'll do the backside. All right, I'm back. Let's look at these last two here. And notice these are higher degrees. So these are fourth degree. So here, I know I'm going to have 4 zeros in all. If I use that rational zero theorem, the possible rational zeros would be all the factors of 9. So I'd have plus or minus 1, 3, and 9 only. And all of these are sort of boring examples because the leading coefficient is 1. But, if there were more than one leading coefficient, we've seen how to do that. We have to divide by each one of these. So this is just 1. So here are our 1, 2, 3 times 2 are 6 possibilities. So again, we can go ahead and graph this. Notice this time, since we have a fourth degree, we need to find 2 zeros to bust it down to a quadratic. So I'm going to show you how to do that. Here is my graph. I notice that this is coming down, it's hitting, coming back up, and it has a little wiggle here. So I have to be really careful here because it only looks like I have 1 0 that I could see. Now, I could go ahead and zoom in on this to see if it actually crossed and went back, but I think I know, and I think you might know what's happening here. It's actually bouncing off the axis. So we see this 0 at perhaps negative 3, which is on our list. So let's go ahead and trace and put in negative 3. Yep, it's exactly 0. So since this bounces off, we know that this is going to have even multiplicity. So that 0 here, negative 3, is going to be used at least twice. We can do that to our advantage to get the factors here. So I'm going to divide in negative 3, not just once, but twice. So my factor is 1, 6, 10, 6, and 9. Multiply, add, multiply, add. multiply, add, multiply, and add, and we do get a 0. So yep, x equals -3 is a 0, just as we thought. This is going to be a polynomial of degree 3, so it would be x cubed plus 3x squared plus x plus 3. But I saw on my graph that we did have a bounce there, so I know that we can try -3 again. Let's do it. So I have -3. We use this new polynomial, so bring down, multiply, add, multiply, add, multiply, add. Just like we thought, it worked. So we have x equals -3 is another 0. What that gives us for factors, the factor for x equals -3 is x plus 3, and there's two of them, so it's x plus 3 squared. And then here we have an x squared plus 0x plus 1. All right, so I'm going to take this last polynomial here. It doesn't factor, but I can use the quadratic formula, or this one doesn't have a middle term, so why not use that square root method? I'm going to subtract the 1 over. I'm going to take plus or minus the square root of -1, and that gives me another imaginary pair. So two complex conjugates. So in this case, I see that x is equal to plus and minus I is 0, and then x is equal to -3 is a multiplicity to 0. Counted twice. So if I'm factoring this out altogether, I get x plus 3 squared times x minus I times x plus I. That would be the factored form of that polynomial. I just want to show you something once again. You sort of notice this little twist up here. So sometimes it's evident that even though the polynomial doesn't go through the axis again, when it has this twist or the turning points, so it can have, it's a fourth degree, it can have as many as 3 turning points. So here's one turning point, there's 2 turning points, and there's 3. When they have these turning points up here that were off the axis, those actually do symbolize these imaginary units. Sometimes it's pretty easy to see, sometimes it's really difficult to see those. Okay. Let's look at our last one. Again, we're looking for 4 zeros here. And in this case, our possible rational zeros are going to be the factors of 12 over the factors of 1. So plus or minus, 12 has quite a few factors. 1, 2, 3, 4, 6. 12. Okay. I guess not as many as I thought. And then when we divide those by plus or minus 1 for the leading coefficient, these are the 1, 2, 3, 4, 5, 6 double 12 possibilities that we get. Let's go ahead and graph this. So I'll go to y equals, and this will be x to the 4th minus 7x squared. So whoops, x to the 4th minus 7x squared plus 12. All right, and we'll graph it. Okay, so I note here, whoa, it looks like there's 2 bouncing zeros here. This one looks like it might be at -2, and this one looks like it might be at +2. So I'm wondering, is this an even function? Yeah, if I plugged in a negative x here to the 4th, that's going to give me x to the 4th, and a negative x squared. That's going to give me x squared. So this is a good example with even functions that I was even thinking about. If I can find the zeros over here, then the zeros over here will be exactly on the other side, because even functions have that symmetry with respect to the y-axis. So that's really helped us in our work. We thought it might be -2, so let's just verify that. So when I do a trace, there it is, and plug in -2, it does give me a 0. Okay, so this one will be sort of intuitive. That's nice. I'm going to do -2, and I'm going to do 1. Now I have to be really careful here because I don't have an x cubed term, so I'm going to put in a 0. I have a -7. I don't have an x term, so I'm going to put in a 0. I have a 12. So these are the coefficients. I have to be really careful to include x cubed and x because I don't have any here. So I'm going to push down my 1, multiply, add, multiply, add, multiply, add, multiply, and add. So yep, x equals -2 is going to work. And we did see that it was sort of repeated. So let's try that second one. Multiply, add, multiply, add. It doesn't look like it's working. Because when I multiply by 5 and I multiply and add, I get a -4. Okay, so that's not going to work exactly how I thought it would. That's okay. I did see that 2 was another 0. So what I'm going to do, sometimes things don't work. And it's a good lesson to just keep trying. So over here, I did see -2. It is an odd function or an even function. So I do know that 2 is going to work. I'm going to use my reduced coefficients here. So 2 should work. So if this doesn't work, we can panic, but I'm just going to try something else there. So maybe I didn't zoom in on the graph enough. I put down my 1, multiply, and I add. I multiply, and I add, and I multiply, and I add. Great. Woo! All right. So we get x equals -2 to work, but it's only for 1, 0. The function is even, so I get x equals 2 to work because it's on the other side of the axis. Now, I have to find those other two zeros. So I have, so far, x plus 2 for that factor, x minus 2 for this factor, and then I have x squared minus 3. That's my factored function so far. If I do x squared minus 3, you know what I'm going to do? I'm going to do the square root method just like I did up here. So I'm going to add 3 over. I'm going to take the plus or minus square root, and I get plus or minus square root of 3. So those are my last two zeros. So I have plus or minus square root of 3, x is equal to -2, and x is equal to 2. Those are my 4 zeros. Notice these are also evenly distributed about the y-axis. So my factored polynomial would be x minus 2, x plus 2, x minus √3, and x plus √3. Now, the reason that we didn't see these zeros, it's a good lesson, on our list is because they're not rational. Plus or minus √3, they're irrational numbers. They cannot be written as a fraction. So I'm going to come back to my calculator here, and what I'm going to do is I'm going to zoom in just to see what's going on here. Hey, what's going on here? And from this view, we should be able to see it. So it did. You can see that there. It did go under the axis. And then since it's an even function, it did the same thing over here. So here's my plus √3. Here's my minus √3. There's my plus 2 and my minus 2. So again, if I plug in something like, do a trace, let's do something like minus the square root of 3. It does give me 0. Okay. So that's something good that we learned there. One, not to give up, and also, when we have an even function, they're evenly distributed about the y-axis. All right, let's take one last break and then we'll wrap things up. All right, I'm back. What we've seen from our examples above sort of give us a blueprint for some theorems that we get. They're called corollaries. They're basically results from these theorems. So for polynomials with rational coefficients, so as long as we have a fraction or a whole number as coefficient, if we have a zero with a square root in it, so if we have an irrational zero, sort of like we had right here with this root 3, then by the quadratic formula, the negative rational zeros are too. So remember, negative b plus or minus 2a. So here's the plus and here's the minus. So if you have one of these, like a plus root 3, you'll also have negative root 3. You noticed above that we had sometimes non-zero imaginary zero. So it was a I should say non-real zero with imaginary part. So if we have a plus bi, the conjugate a minus bi is a zero automatically as well. So we can illustrate this above. Here we saw that we had plus I, so negative I had to be in there. And essentially this comes from the quadratic formula as well. Okay, so now we're going to use these ideas to go ahead and construct polynomials. So the first example here is we're going to find a degree 3 polynomial function with rational coefficients, and we won't multiply out those factors. So when I have zeros, I can actually construct the function using those zeros. So I could say f of x, since x equals 1/2 is a 0, I know the factor x minus 1/2 would be the factor that gives me that 0. I have x is equal to -5, so I have x plus root 5. That's going to give me one of those zeros. Now I'm going to use the theorem above that says, hey, if we have one of these irrational zeros, then the negative one has to be there as well. So if we have negative root 5 is a 0, root 5 has to be a 0 as well. And that would give us x minus root 5 as a factor. This would be a nice function. If we wanted to, we could multiply these out. I might want to rearrange this a little bit to make it like 2x minus 1, but totally not necessary. So this would be a fine function. If I really wanted to multiply through, I could. So I had x squared. I note that the negative root 5x and the positive root 5x are going to subtract out. And then root 5 times root 5, negative root 5, is 5. So if I really wanted to multiply this out, I could. This would be x squared plus 5, x squared minus 5. And then I can multiply these factors out. So the 2x times the x squared, the 2x times the -5, and then the -1 times the x squared, and the -1 times the -5. So if I really, really, really wanted to multiply this out, it would look like this, but any one of these is fine as well. All right, finally, let's look at this last one. I need a 4th degree polynomial with real coefficients that has x equals -2, x equals 2, and x equals I of zeros. And I also needed to go through the point f of 3, so the function at 3 is -150. So let's go ahead and construct this polynomial first. I want you to notice that if I is a 0, then negative I is going to be a 0 as well because of that conjugate 0 theorem up here. So if we have plus I is a 0, then negative I is a 0 from that theorem or the quadratic formula. So when I'm getting my function here, I'm going to have x plus 2, which would give me a 0 at minus 2. X minus 2 would give me that 0 at x is equal to 2. X minus I would give me this one, and x plus I would give me the other one. Yay! So I have a nice polynomial here. Let's go ahead and graph it and see where it goes through. Okay, so when I'm graphing this on my calculator, move it over here a little bit, I have x plus 2 times x minus 2. Oh, wow. So now I have x plus I and x minus I. I really can't put those in. So I should go one more step here. And I'm going to just put in, I'm going to multiply those two together. So I'm going to have an x squared plus xi minus xi, those subtract out. And now if you're really careful, minus I squared is -1, negative and negative is a +1. Okay, so this is what that would look like. I have an x squared plus 1. So this would be some of the reason why you might need to combine those a little bit. All right, and I have this totally zoomed in. I really don't want that. Let's just do a zoom standard for now. I basically want to see if it goes through the point 3 comma negative 150, and you can see that it doesn't. So if I do a trace and I plug in 3, it's 50. Okay, so it's way up here, but I want it to be negative 150. So we sort of know what's going to have to happen here. Just like when we did with the quadratics in vertex form, what we're going to have to do, we don't want to add something on because it's going to move this up and down and it's going to change the zeros. So what we're going to do is we're going to multiply it by something that stretches it vertically, and it might flip it. In fact, it will flip it, right? So that 0 or that 3 comma negative 150 will be down there on the graph. Let's go ahead and do that. So I have my function f of x is equal to this. I'm going to put in a stretch a. I'm going to use this point 3 comma negative 150 to find that stretch a. So negative 150 is equal to a times 3 plus 2. 3 minus 2. 3 squared plus 1. So negative 150 is equal to a times 5 times 1. 9 plus 1 is 10. Negative 150 is equal to 50a. And when I divide by 50, a turns out to be negative, which we knew it was going to be. In fact, it's going to be a negative 3. When I plug that back into my function up here, my function that I should get would be negative 3 times x plus 2, x minus 2, x squared plus 1, without multiplying everything out. Let's go ahead and just check that out to see if it works. So what I'm going to do is I'm going to try to be a little slick here. We'll see how it works. I'm going to say, all right, that stretch was negative 3, and then I'm going to multiply it by y1. So to do that, I go to variables. I think I can show you here maybe. There we go. Variables. I'm going to go down over to y variables, and I'm going to put in y1. So that should take negative 3 times what we have up here, and it should show them both. Now, when I graph it, I'm going to do a window change so I can show you all what's happening here. I'm going to go from negative 5 to 5 on my x-axis, and the scale is fine at 1. But now I know this graph goes way down there, so I'm going to do negative 200 to 100. So my scale is a little bit off there. I'm going to go in steps of 10 there, just to show you what's happening. All right, so when I graph it, there is my original function. We know that doesn't go through 3, 150. But my red function goes to the same zeros, and it should go through that point. So if I go to my red function, do a trace, and go up to my red function, if I plug in 3, I should get negative 150, and sure enough, it's there. So what that's done, that negative 3 for the multiplier has basically flipped the function and stretched out vertically by a factor of 3. So we do know if we did the blue function and we plugged in 3, we got 50. Okay. All right. Long section, but I hope this helped you a lot. I hope it was worth it.